All right, this is Physics 1C for March or October 18th, and we're tonight going to be going over some more problems with Kirchoff's rules that we learned about last time. We're going to talk about RC circuits. These are circuits that have resistors and capacitors in them. And then we're going to get into magnetism, which will be kind of a whole new set of topics here, talking about where magnetism comes from, the magnetic field of the Earth, what magnetic poles are, what magnetic monopoles would be, and then into the discussion of what magnetic force is, magnetic field and flux, and so on and so forth. So a lot of topics to get through today. We've got 3 hours. Let's see how much we can get through. So I wanted to do 2 problems involving using Kirchhoff's rules, okay? And I'm just going to go ahead and remind you what we learned last time. Johnny, I just saw your question. Is it possible to make the current one due tomorrow for the homework? Yeah, that's fine, I guess. This one? You want me to move it to here? Okay, that's fine, I guess. That one's really easy, though, honestly. I mean, I know that the homeworks don't seem really easy to you all ever, but that one in particular is a pretty easy one. All right, so right, what did we learn last time? We learned that there are 2 rules that we call Kirchhoff's rules, and what they are: there's a loop rule and a junction rule. Okay, the junction rule says that if you sum all of the currents flowing into a junction, they should add to 0, and the loop rule says if you sum all the voltage drops around a loop, those should add to 0. Those are the 2 rules. And in order to use them, we need to have some rules for how we approach our circuits. So to give you an idea of how that works, suppose that we have a loop that we're traveling around, and we travel from the positive side of the battery to the next negative side of the battery. Then what we get out of this is that the battery has an EMF of E. Then this gives us a contribution of delta V equal to, what is it, negative E or positive E? If we travel to the left from the positive to the negative, do I put negative E or positive E for this one? Do you all remember? And then what do you get when you go from the negative? Okay, this one's negative E, right? And this one on the right is positive E, right? Okay, there were 2 other rules that we needed for this. Those were the ones in which you had a resistor. So if you have a resistor here and a resistor here, and there's 2 possibilities now because now there's going to be current. So we have our resistor, okay? And let's say in this one the current is flowing this way. Let's say in this one the current is flowing back this way. And then there's one other piece of this, which is what direction are you traveling in. So let's say you're traveling in the same direction as the current here. You're traveling against the current here. When you travel in the same direction as the current, you're going downstream. So the potential drop is IR, but it's negative. And here, when you go up against the current, you get positive IR. And those, all taken together, are Kirchhoff's rules for handling and understanding circuits. So I wanted to do this problem here because I know that there's problems in your homework that's like this, and it's not something we talked about yesterday, where they ask you to find the potential between 2 points here. So it says, in the circuit shown, find A, the current in each branch, B, the potential difference of point VAB relative of the potential difference VAB of point A relative to point B. So this separate little question here is something I hadn't addressed yet, and I wanted to make sure that we talked about. So let's do that. Okay, so we're going to analyze this circuit right here. So I want you all to take the time to redraw the circuit on your own paper so you can follow along with what we're doing, and I'll do the same thing right here. So draw your own circuit on your own piece of paper so you can actually try to solve this. I'm going to draw it down here. we drew our circuit. What's the first thing that I want to do when I want to analyze one of these problems? Draw loops, that's wrong. Current. Determine the series. Pick a direction with the current. It's all kind of it has to do with the current, yeah. So, current. We need to label some currents, right? We need to label some currents. That's the first thing we want to do. So step 1, label currents. So we're free to do this any way we want to, right? So what I'm going to do is I'm just going to go from top to bottom, 1, 2, 3. And I'm just going to call them I1, I2, I3. And I'm not even going to think about in any way what direction I want them to point. I'm just going to say this is going to be I1. This is going to be I2 flowing through here. And this is going to be I3 flowing through the bottom. Okay. I1 will, of course, continue all the way through here. I2 will continue all the way through here as well. And I3 all the way through there. Okay, so I'm going I1, I2, I3. It does not matter what direction you pick. So if you're trying to do this problem yourself, make sure you pick the same directions as I picked. That way you can compare and we can have our equations be the same. The second thing to do is what George said, which is to draw loops. Okay, any questions before we move on to step 2? Okay, same thing here. We can choose these as we please. So I'm going to make one loop go this way, around this way. So that's going to be my loop that I call loop 1. And then we'll have a second loop, which I'll use another color for. What color do I have left? I don't have enough color options up here. Blue? I have enough blue. And this will be our bottom loop down here. Okay, so the bottom loop is going to go like this. Like this. I'm going to call that loop 2. We could, in principle, also draw another loop around the outside. So we'll draw that one just for good measure. This will be loop 3. And we'll write down all equations and just talk about them. So we've drawn the loops, okay? And now basically step 3 would be to use the rules. We'll say the junction rule first. And then we'll do the 2 loop rules. Okay, again, we call this the loop rule. We call that one the junction rule. Okay, so let's pick a junction to do the currents for. Let's choose this junction right here. Okay, you can't choose a corner. You got to choose a place where the currents all meet. Now, from this junction, all 3 of my currents are going out. Okay, and so I'm going to write that my equation here is going to be negative I1 minus I2 minus I3 is equal to 0. I'm making all of them negative because they're all going out of the junction. So I1 goes out like this, I3 goes out like this, and I'm just defining it so that outgoing currents are negative. You can obviously see that we could multiply through the whole equation by a negative sign and just get I1 plus I2 plus I3. That's because if you came over to this junction, that's what you would get, because at this junction, I1 is coming in, I2 is coming in, and I3 is also coming in, right? So at this junction, the rule you would get would be I1 plus I2 plus I3 equal to 0. Does that distinction make sense to everyone? Okay. Now we go for the loop rules. This one's the easiest one to do. The loop rules are always a little more tricky. So we'll do loop 1. And we're just going to follow these rules up here. Okay, all the rules that are contained within that box right there. The purple line represents the direction we're traveling. Okay, I'm going to start. Let's start at this point right here for our loop 1. So we're going all the way around back to the same point. So I have a 4 ohm resistor right here, and I know the current flowing through it is I2. Our direction of travel is this way, but the current is in the opposite direction, so that corresponds to this picture right here. So we're going to write down positive IR. The current is going to be positive I2, and then we multiply by the resistor, which I'm just going to write 4 ohms. Okay, positive because the direction of travel is to the left, while the current is back to the right. They're opposite, so we use a positive sign. We go to the battery right here. We're going from the negative side to the positive side, so that corresponds to this picture right here. So we're going to write positive 5 volts. That's the EMF. We get to this right here. We again have a 1 ohm resistor with the current flowing opposite to the direction that we're traveling around the loop. So we're going to write plus I2 times 1 ohm. We continue around to the top of the loop where we get to this resistor right here. Now we're traveling in the same direction as the current, so we're going to write minus 2 I1. So I'll write I1 times 2 ohms. And then we get to the battery. We're going from positive to negative, so that's like this right here where you write negative E, which is negative 10 now. And finally, this piece right here where we have 3 ohms times I1. And we're going in the same direction as the current again, so we're going to write negative I1 times 3 ohms. Okay, so to go back through them again, as we went across the 4 ohm resistor right here, the path and the current are opposite to each other. The direction of the loop and the current are opposite to each other, so we write plus IR. It's a 4 ohm resistor. The size of the current we called I2. Next, we go to the 5 ohm. We're going from the negative to the positive side. We look up here and see that when we go from negative to positive side, they give us a plus E. So we write plus 5 volts there. When we get to the 1 ohm right here, we're going against the current again because we're traveling this way and the current's opposite to us. We need to write plus IR. It's I2 times 1 ohm. That's IR. We get to the top. Now the current in this branch is I1. We're traveling in the same direction. So you get a minus 2 I1. You get a minus 10 volts. And you get a minus 3 I1. The reason why you get minus 10 is because this is the plus side of the battery and that's the minus side of the battery. And so when you go from the plus to the minus, you get negative E. Okay, hopefully everybody can write down that equation. This should all sum to 0, right? Any questions? We can combine, we could basically divide through by an ohm, so we don't have to write ohms every time. We can combine like terms, so if you think about it, it's 4 plus 1 or 5I2, 3 plus 2 or negative 5I1. You can see that in the equation as well. And then I'm going to take there's a 5 volts minus a 10 volts, which will be negative 5. I'm going to add it to the right-hand side so we can write our equation down like this. And this is the equation for loop 1 now. All right. And volt over ohm, what unit does that give me? What is volt over ohm the same thing as? Amps. Yeah. So we just write that one as the amps. Okay, let's do number 2. Okay, I did that one. Why don't you all take some time and do it yourself? I'm going to give you not much time. I'm going to give you like 2 minutes. Go. 2 minutes. Write down the loop rule for loop 2. All right, 2 minutes. Write down the loop rule for number 2. All right, that is 2 minutes. So hopefully you were able to figure this out. Oops. Stop. There it goes. Okay. So I'm going to start down here, bottom left corner, and we're going to go around. On the bottom one, we have 10 ohms, I3. So I'm just going to write I3 times 10 ohms. Is it positive or negative? Well, we go this way is the loop direction. That way is the current direction. They're opposite. So that means we're going upstream. We put a plus. Going back around to the middle here, now we have 1 ohm times I2. So we have I2. We have 1 ohm. Is it positive or is it negative? The loop direction is to the right. The current direction is to the right. They're the same. So we put a negative sign because we're going downstream. So that's a drop in voltage. Coming to the 5-volt battery, it's going to be negative 5 volts because we're going from the positive to the negative side. And then finally we have the 4 ohm resistor right here, which has current passing in the same direction. So we're doing the bottom loop, right? I wanted to make this blue. Let me fix this. I want to make these the same color. We're doing the blue loop, right? So along the blue loop, we're going to the right. The current is also in the same direction. So we're going to write a negative I2 multiplied by the resistance, which is 4 ohms. Did everybody get the same answer? Did anyone get the same answer?
I think I got the same answer, but I started at the EMF, so I started with like minus 5 volts. Does it matter?
I mean, what do you think?
As long as you get the signs right. No, I don't think so, but that's the tough part.
Yeah, exactly. It doesn't matter where you start. You should get the same answer. Yeah. The order doesn't matter, right? Because I could take this and I can move it anywhere I want to in my equation, and it will still say the same thing. So now we're going to group terms again. So we have I2, there's a 5I2. So we'll write negative 5 I2. And then we have 10 I3, so plus 10 I3. And that should be equal to the negative 5, we move it to the right-hand side, 5 volts, but we divide by ohms, so we get 5 amps. Hope that part's not confusing everyone. Definitely like to have the units work out and, get rid of as many symbols as we can, ideally. Okay, finally, we are going to draw the loop rule for the outer loop. And again, I'm going to start at this point right here, and we're going to go all the way around. Now, well, we'll just do it. So again, we're going to start off with 10I3. I'm not going to write any of the resistances for this one, the ohms. So we get 10I3. We go up this way. We come to this one. We get negative 2I1. But we see down the line we're also going to get a 3I1 from this one. So I'm just going to combine those together and say negative 5I1. Right? Negative 2I1, negative 3I1 will add to negative 5I1. And then we have a 10-volt battery right here. So that's going to be, we're going downstream with that, right? Negative E. So we write negative E for that, which is negative 10 volts. And I've already divided through by the ohms, so I'll put volts over ohms. That should be equal to 0. And rearranging it and putting it in the order of I1 to I2 to I3, I'm going to write negative 5I1 plus 10I3 is equal to positive 10 amps. So we get this other equation. This is our third loop equation. All right. Now, how many unknowns do we have in this problem? How many unknowns do we have? Come on, let me write. Yeah, there's 3 unknowns, right? I1, I2, I3. So, yeah, we're going to use a matrix to solve it, but actually, this one we don't really have to because the coefficients are really nice. But anyway, it doesn't really matter. Those are our 3 unknowns. How many equations do we have? We have 4, right? Junction rule and 3 loop rules. How many do we need to solve? If I have 3 unknowns, how many equations do I need? to solve for those unknowns. 3, right? 3. But we have 4. So how do we pick? If we have 4 and we only need 3, how do we choose which 3 we're going to use? Which 3 to use? Do we use the junction rule in the first 2 loops? Do we use 3 loops? Do we use the simplest? Okay, that's mathematically there. I don't know. I mean, I guess simplest. Okay, they're all pretty simple equations, I think. First 3 loops. Okay, so we don't know the answer, which is the point here, right? Does anyone have a definitive answer? Anyone have a strong reason why they would choose, or do we just go with any 3? Should any combination work? 1 junction and 2 loops. Giselle's saying the same thing. Use the first 3. You don't want to work with a junction because they're all unknown. Any combination. Okay, well, in that case, I'm going to choose to do what Evan said, not for any reason other than educational purposes. We're going to try the 3 loops, okay? We're going to try equation 1, equation 2, and equation 3, all right? And here is how we are going to do that. So I notice when I look at these equations that if I were to add equation 1 plus equation 2, that would actually eliminate I2. Can you all see that? That if you do equation 1 plus equation 2, what you get is these 2 cancel, and you get negative 5I1. Wait a minute. Should I show this? I don't know. Sometimes, even if I think something's simple, it's a good idea to actually show the steps. So I'm taking this equation, right? And we're going to stack at it with this equation. So I'll just put it underneath it here. So we're taking equation 1 plus equation 2, right? So now we add these 2 equations together, and what do we get? Well, the first thing we notice is that positive 5I2 and negative 5I2 are going to cancel with each other, right? So what we have then, total, does anyone already see what's going to happen? You get negative 5I1 plus 10I3 is equal to 5 plus 5 is 10. This is the same thing as equation 3. It's the same thing as equation 3. So now what can I do? Can I now take this equation and plug it into this equation? Is that going to work? It's not going to work, right? I can't just solve this one and plug it in here, right? It's not going to work. What happens? I'll just show you what happens if we try it. So say that we try to plug the equation back into the same equation. This equation can reduce down to, if I divide through by negative 5, what I'll get is I1 minus 2I3 is equal to negative 5, right? Or negative 2. So all I did was I just divided the whole thing by negative 5. So that means that I1 is equal to 2I3 minus 2 amps, and then I can plug that into this equation, right? So that equation says negative 5 times I1 plus 10I3 is equal to 10. So all I'm doing is I'm basically taking this I1 right here, plugging in for I1 right here. Now what do we get? On the left-hand side, we get negative 10I3. Negative 5 times negative 2 is positive 10. And you all may have seen this happen before when you do algebra, where you basically get something that says 0 equals 0. Right? Because this cancels with this, and this cancels with this. And this equation doesn't mean anything. So, that's a problem, right? That's a problem. So the answer is that you cannot ever use all 3 loops. That is not allowed. You can, however, use the junction rule with any of the two loops. So I can use the junction rule with 1 and 3, 1 and 2, or 2 and 3. There's 3 possible combinations, right? But you cannot use just the loop rules. That's the lesson to be learned from that. And the reason why is because no matter how you choose your loops, it doesn't matter how you choose them, one of the loops is merely going to be a linear combination of the other 2 equations. So these 3 equations are not linearly independent. That's the problem. For those of you that have taken, I think it's linear algebra where you talk about that, right? Have any of you taken linear algebra? Usually there's a few people, right? And you learn in linear algebra that if you want to solve a set of equations, they have to be linearly independent. Does that sound familiar to you all? That the equations have to be linearly independent? Yeah. So this is an example of, and I'm sure that those of you that have taken it noticed immediately that as soon as you added these 2 equations and you got this same equation, you knew that it wasn't going to work, right? Because this isn't any new information. It's simply the sum of these 2 equations. So it's not it's not a new equation that tells us something about the relationship between the variables, because we already knew that relationship, because we could have just added them together. Now, that being said, can you see why from the picture that happens? If you look at your picture right here, if you look at the way we did our loops, right? Loop 1 is a circle like this. Loop 2 is a loop like this, right? If you look in the middle, those 2 loops are going in the opposite directions, right? When we went for loop 1, we went to the left through this branch. For loop 2, we went through the right through this branch. So that's why the I2s are the things that canceled out when we added the 2 equations together, because that was the piece of our loop that was common. And if you break off those 2 pieces of the loop and combine them together, you get the big loop, pretty much, if that makes any sense. All right, so we know this doesn't work. I'm going to take this out of the notes because it's not important, and you all can do it yourselves. But let's solve it the proper way. Evan said we can throw these into a matrix. That's true. So let's construct the matrix that we would use for this equation, and then I might solve it by hand, because this one actually is pretty easy to solve by hand, as it turns out. So the matrix that we would construct for this would look something like this. So the first equation up here would be, and remember, this is how you do this. So you write I1, I2, I3, and then over here you're going to have your constants, basically. So the coefficient for I1 goes right here. So in the loop equation, that's -1, or the junction equation, that's -1, -1, -1. So those are the coefficients for I1, I2, I3, and that's equal to 0. For this one right here, for the first loop rule that we're going to use, we're going to write -5 for I1, +5 for I2, and then what do I put for I3? The coefficient of I3 would be 0, right? And then on the right-hand side, we have 5 amps, so we just put a 5 right there. And then we use loop number 2, and so we'll have the coefficient of I1. There's no I1, which means the coefficient is 0. Coefficient for I2 is -5. Coefficient for I3 is +10. And then on the right-hand side, we have, again, 5 amps. It's really 5 for both of them. Interesting. So that would be our matrix that we want to use. And then we have to throw this into a reduced row echelon calculator. So I'll do that real quick. You all can do it on your TIs if you have one. I really should just get a TI-83, honestly. I really should. All right, let's go out of full screen here so that this doesn't... No, that works. So I'm going to throw this into my calculator here on the left. And again, I would show you, but apparently it makes it so that my videos get removed, so I can't do that. -5, +5, 0, 5, 0, -5, 10, -5. Calculate. We get as answers for this one -0.8, 0.2, and 0.6. So the output is, you always get an output that's like this. You get an identity matrix in the first 3x3 thing, and then you get answers here: -0.8, 0.2, and 0.6. Why does it say times a? Did I accidentally put... No, that's interesting. So this tells us that our answers... Sorry, I didn't mean to do that. This tells us that our answers are I1 is equal to negative 0.8, I2 is equal to 0.2, and I3 is equal to 0.6. And we should be able to prove by using regular math. Does it work with a TI-30? It does not. No, you need to have like a TI-83 or something like that, which like I can give you during the exam. So if you don't have one, it's fine. I'll give you a calculator that can do this for you during the test. That being said, you need to learn how to use it. So if you haven't used one before, during your next lab period, if you want to come ask me, I'll show you how to do it. Pretty much what you do is you go into the matrix editor, you type in your matrix like this, and then you go to the screen and you just put RREF and then put your matrix in there, and then it pops out the answer. It's really easy to do. Anyway, so that's what you get as your answers. Just to show that we could get the same thing, let's grab these equations here and let's solve them in the so-called normal way. So these three equations here, I'm going to solve these. Move this down. Get plenty of room. All right, so if we want to solve those three equations by hand, easiest way to do it, keep in mind you do not need a calculator to do this for you. It's a good way to check your answers. Okay. So what do? I think the easiest thing to do is just solve for each of our variables and sub them in. There's an I2 here and there's an I2 here as well. So we're going to solve for I1, solve for I3, and then plug in. So in this equation here, we can divide through by -5, I guess. So we're going to get I1 is equal to 1 amp negative. This becomes negative, so it's going to be positive over here. I think that's what that one becomes. Divide through by 5, by -5. This will become negative I2. We'll add it over, divide by negative, you'll get that. In this equation here, if we want to solve for I3, what we're going to get is, so what would be 5 amps plus this, then we divide by 10. So you're going to get 0.5 amps plus 0.5 I2. Does that look right? Yep. Yep. And then we just take both of these and we plug them into this equation. So we're going to get negative I1 is negative 1 amp plus I2 minus I2. That's the one we're not changing. And then minus I3 equals 0. So we end up getting positive 1 minus I2 minus I2 minus 0.5 amps minus 0.5 I2 is equal to 0. We'll group everything together. So what do we have? Negative 2.5 I2 is equal to 1.5 amps. We then divide both sides by, let me make sure I did that right. Positive 1, no, I didn't do it right. Positive 1 minus 0.5 is negative, no, positive 0.5. So this is going to be equal to negative 0.5 amps. There we go. Okay, which means that I2 is equal to 0.5 negative divided by negative 2.5 amps. If you multiply by 10 over 10, this would be, I mean, it's going to be 0.2, right? Because it's like 5 over 25, which is like 1 over 5, which is like 0.2. Oops. 0.2 amps would be what I2 would be equal to. And if we go back to this equation right here, this tells us that I1 is then going to be equal to I2 minus an amp. So that's going to be negative 0.8 amps. And then finally we have I3, which is going to be equal to 0.5 amps plus 0.5 times I2. So if I divide this by 2, I'll get 0.1 plus 0.5 will be positive 0.6, which you can actually see still from above is what the answer is supposed to be for this one. And we can go back and we can check. According to our matrix method, the answers were I1 is equal to negative 0.8. That's exactly what we got. I2 is equal to 0.2. That's what we got here. And I3 was equal to 0.6. So we got the same answer with both methods. which is one of the really nice things about this method. You can check your work by doing it. You can do both ways and, do it both ways until you get the same answer with both of them, then you know the right answer. You got the right answer. Okay, does that make sense? Does anyone have any questions? Just to summarize, you have to use the junction rule and then any two loop rules. Okay? Junction rule plus any two loop rules. That's the way we do these. All right, now what I want to do is I want you to take some time. We'll give you like 5 minutes or so. I want you to try to set this problem up right here. Set this one up. So this one is different because there's 4. Oh, we didn't finish. We're not done. We're not done with this one. My bad. The whole point of doing this one was now to go back. Let's look at what it says. In the circuit shown, find A, the current each branch. Check, we did that, right? And now it says to find the potential difference VAB of point A relative to point B. Point A relative to point B, okay? So let's put those points onto our picture now. So point A is here. That's A. And point B is here, right? Yeah, it makes no difference what direction you pick, Tanbui. Try it yourself. Convince yourself that that's true. But yeah, you'll get the same answer. It doesn't matter which direction you pick for your loops. It doesn't matter which direction you pick for your currents. You will always get the same answer. Now, if I had changed the direction of my currents, like if I made I1 point to the left, the equations would look different, but the answers would be the same, except that this would have been a positive number. Okay? So I picked I1 to the right, and my answer was negative. If I had picked I1 to the left, my answer would have been positive, but that's the same thing, right? Hope that's not too confusing. All right, we need to find the potential of point A relative to point B. This is actually very easy to do. All you have to do for this is to draw a new loop. I'll use this rainbow color here. So we want A relative to B. So I believe we want to do a loop where we go basically like this. And then we just stop right there. Okay? So we start at point B and we go to point A. And we write down our loop rule. Now there's not much room here. I'm going to write it in this little space right here that we have. There's not much space, but I'm going to write it right here. We don't need this anymore. You will understand that. I can put it right here. Okay. Part B, we want to find the potential of point A relative to point B. Okay. So we're going to do this little loop equation. We're going to start from here, and we're going to go to here. That should give us the potential of point A relative to point B. So what do we have? We have I2 flowing to the right. The direction of my loop path is going to be this way, because I'm going from B up to A. And now we write negative 4I2. And then we come around to here, and we get positive 3I1. And it's saying that that should be equal to the potential of point A relative to point B. You can get the same thing by going the other direction, by the way. You get the same thing. So if I instead went around like that, you could get the same answer. But as you can see, there's more things to write if we do that, so I'm not going to do that. So this is equal to negative 4 times I2. Let's use the actual units now. Negative 4 ohms times I2. I2 is 0.2 amps. Plus 3 times I1. I1 is negative 0.8 amps. This should be equal to VAB. Oh, I should have this set up. I bet I'm getting cut off here, aren't I? I probably cut that off a little bit. Oops. Go down a little bit. That's better, right? Yep. So that tells us that VAB is equal to... Okay, 4 times 0.2 is 0.8. 3 times 0.8 is negative 2.4. So negative 0.8 plus negative 2.4 would be negative 3.2, I think. Is that right? You'll tell me if that's right or wrong. Is that, yes, you're saying, George, to what I just wrote? 0.8. Yeah, that's like 1.8, and then that's 3.8s. So 4 times 0.8 would be 3.2. Yeah. Negative 3.2 volts. The other method would be to go this way. Do you all want me to do the other method? I'll leave that for you to do yourself. Start from point B, you'd write 5 volts plus 1 I2. I2 is 0.2, so 5.2. And then minus 2 I1. So 5.2 minus 2 times negative 0.8. So you're really adding 1.6. So 5.2 plus 1.6 is 6.8 minus 10. You get exactly the same answer. You get negative 3.2 volts. So whether you go from B to A to the left or B to A to the right, you will get the same answer. So again, you can kind of, yeah. So you'll see the stuff show up on your homework. I just wanted to make sure you'd seen it before. That's all. Anyone have any questions? Have you all seen those type of questions on your homework already? I guess it depends on how far ahead you've gone. This is on the DC circuits homework. This is the one that's due next week. In fact, questions like that may actually appear even on the homework that's due tonight, or now it's due tomorrow. But one thing I wanted to say is that if you're struggling on any of the more complicated problems from the homework that's due this week, be sure that you just use Kirchoff's rules, okay? It definitely is a simpler way to solve some of the problems. So don't be afraid to use Kirchoff's rules. All right, that's a really good problem. But we want to do one more, just to make sure that you all really understand how to do this stuff. We're going to do one more of these, because I don't want anyone to have an excuse that we didn't, there's not going to be enough room for all this stuff at all. So I want you all to try to solve this problem right here, okay? In fact, what I want to do is, I'm glad it's helpful. That's good to hear. I'm going to try to paste this in here. There we go. That way, in case for some reason you're looking at this on your phone, you want to make it bigger, you can. But what I want you to do is I want you to write down the junction rule and the loop rules in this case. How many loop rules are we going to need? There's 3 different segments, right? So we're going to need 4 equations, but there's going to be 3 rules. Okay, so just to make sure we're all on the same page, because if we all pick different directions for currents and stuff, it's hard to compare notes. So what I want you to do is I just want you to label the currents as being I1 like this. I want to emphasize how little time I think about this stuff. I'm just like, let's make them go all up, okay? I'm just saying, make them all go up. Like this. And one other thing that you're going to need, why did I call that I5? This will be I4. You're also going to need to define, even though there's no resistor in this portion of the circuit, and there's really no point in doing this, you need this to be able to... So I'm going to say that in this segment right here, just call the current here, just call it I, okay? You can call it I5 or whatever you want to call it, all right? And what I want you to do is I want you to do the loop rules. So our loops are going to be, one loop is going to be here. That's going to be loop 1. We're going to have another loop that's going to be here. Okay, that's going to be loop 2. And then loop 3 will be in this one here. So that's going to be loop 3. So all of them are clockwise, right? And I just want you to write down the equations. You don't have to solve them, okay? So write down the junction rules. You're going to have 2 junction rules. There's going to be one junction here, one junction here. So we're going to call that 1 and 2. All right, so 2 junction rules. That are going to turn into one equation. You're going to combine them into one equation, okay? And then you're going to have 3 loop rules. Now in this problem, there's actually a lot of possible loops. You've got these 3. You've got the loop that goes around the outside, that's 4. But you could also make a loop like this, for example. And you could make a loop like this, for example, too. So that's another 2 that you could have. So there's a total of 3 plus 4 5, 6 different loops that you could possibly use. We only need 3 of those loops, okay? So 2 junction rules, which is going to turn into 1 equation, and 3 loop rules, which will turn into 3 equations. And our unknowns, of course, are then I1, I2, I3, and I4. And our goal is to calculate what all of these are equal to. So I'm going to give you like 5 minutes, let's say. What time is it? 14:05. We're at that point where we kind of need to be thinking about taking a break. We don't have to take a break yet. So what I'm going to do is I'm going to give you a timer for 5 minutes. 5:00, play. And I want to see if that's enough time. So write down the 2 junction rules and the 3 loop rules for this. If you have a hard time seeing it, you can look at the link that I put into the chat. All right, 5 minutes. Feel free to ask questions in the chat. I can answer them as well. Ignore that. Wait, did it replace my timer or something? Well, that's stupid. You should have 1 more minute. I'm trying to figure out how to get this other timer back, though. Oh, there it is. I'll just give you 2 more minutes. That's the easiest thing to do right now. All right, that's a little over 6 minutes. So let's try to trash. Okay, let's try to. I hope that was enough time to get some of this. Honestly, just as long as you're spending a little bit of time actively thinking about things, you learn a lot more than you do if you're just passively sitting there, you know? It's just how things work. Okay, so let's go through these one at a time. Let's start with our junction rules. The junction rule for this one right here, junction 1, okay? We'll call it J1. Junction 1 is going to be I1 coming in, I2 coming in. Those are going to be positive. And then I going out, so that's going to be negative. For junction 2, right here, we got I3 and I4 flowing into junction 2, so that means we're going to write I3 plus I4, ingoing currents, I'm going to call positive. And then I1 is also flowing in, so we'll put plus I equal to 0. To overthink? Yeah, I understand that. It's a very common problem, especially with Physics 1C, that people overthink things, but you kind of just got to learn the rules and stick to the rules, and any questions you have, you can ask the questions, and I'll try to simplify things for you. Okay, junction 1 and junction 2. Any questions about that? These are the easy ones, really, to do. We combine these two equations together by doing equation junction 1 plus equation junction 2, which is going to lead to I1 plus I2 plus I3 plus I4 is equal to 0. All right. Technically, these 2 points on the circuit, in a weird way, are kind of the same point. Like, this circuit could have been constructed like this, and like this, and it would literally be the exact same circuit. Can you all see that? Is that obvious? I don't know. It's probably not obvious. The point is that if you were to calculate the potential difference between this point and this point, the answer would have to be 0. Can you all see why? Why would that have to be the case? Why would the potential difference between these 2 points have to be 0? There's no resistors in here. There's no batteries in here. Which means these are basically the same point in the circuit. In fact, if you hooked this circuit up, you could hook them to the same point and it wouldn't change anything. There's nothing in here, so it's just a wire, right? And with nothing in there, that means that they have to be the same potential. Anyway, all right, so we get that. That's one equation. Box it in. Next, we do the equation for loop 1. I'm going to go through these relatively quickly here so we can get on to more things today. And because I assume by now you kind of are starting to get this. So with I1, I'm going to start in this corner right here, and I'm going to go that way. So we're going clockwise around here. So I'm going to write negative 200 I1 coming around here. I have 40 volts. We're going from positive to negative, so that's going to be negative 40. I'm going to be dividing through by ohms again, so I'm just going to write 40 amps. And then we go this way, I2, positive 80 I2 equals 0. And then we rearrange this equation. So it's going to be negative 200 I1 plus 80 I2 is equal to 40 amps. And that's loop 1. Okay, look at your loop 1 and check to see that you got the same answer. Did other people get the same answer? And of course, it may look a little different depending on where you started. That's not important. What matters is that your final equation, when you write it from the I1 up to I4, in that form, we should all agree on this final equation here. That's what matters. Okay. All right, next we do loop 2. So here's loop 2. Let's start from that point right there and go around. So I'll have negative 80 I2 plus 40. Again, we're dividing through by ohms, so we get 40 amps. And then we come to this. So we're going in the circle like this, right? We went up this branch. Now we're going down the branch with I3 in it. So we're going from negative to positive, so that's going to be plus 360 volts, but we're dividing through by ohms, so we get amps. And then I3 will be plus 20 I3 is equal to 0. Let me shift this one over to the left a little bit so I have enough room to rewrite it. That is going to turn into, so we have negative 80 I2 plus 20. This should have been a 20 I3, my bad. Let me fix that. Plus 20 I3, my bad. This equation will become negative 80 I2 plus 20 I3 is equal to, we have positive 40 and positive 360, which is going to become negative 400. Okay, do you all agree with that one? Great, and then now we do number 3. Number 3, we'll start at this corner right here and go around in a circle. So we're going the same direction here, so we have negative 20 I3, negative 360 volts, but again, we're dividing by ohms, so we get amps. And then we'll have a negative 80, and then I4 opposite, so plus 70 I4. And this one will become negative 20 I3 plus 70 I4 is equal to, now we have negative 360 plus 80, so 36 plus 8 would be 44, so 440 amps. All right, any questions? Does everyone agree? Just shove this junk off to the right. Use it when we come back. All right, so let's solve this thing. All right, this time we'll solve it by hand first, and then we'll check it with the calculator second. So we need to combine those 3 equations. Luckily, once again, this is pretty easy to do because what we can do is we can rewrite individually each one of them in terms of their... all right, so there's the first equation. There's the second equation. Third equation. And of course, this equation. Oh, that didn't quite get everything, did it? Almost. This equation. Copy, paste. Okay. So those are our equations that we want to work with. Let's zoom back in a little bit. Let's get rid of the little boxes here. All right, so no, I want to click on this thing. There we go. All right, so we'll just go with the same process. It looks like, oh, my process from before isn't going to work, is it? This one's trickier. Let's see what we can do. All right, so this equation here can be solved for, how about canceling I2? Yeah, I can see that I2 can cancel out. I can see that I3 can cancel out if we were to add the equations together. But we don't really want to cancel them out because we want to use this equation here. So I think what I'm going to do is use I2 as my kind of like, either I2 or I1. I think it's going to be I2, I guess. So let's solve this one for I1. This will give us I1 is equal to, let's do this in 2 steps. So 40 amps minus 80 I2 all divided by negative 200, which is going to be 4 over 20 is the same thing as 1 over 5, so that's negative 0.5, or 0.2 amps, I believe. And then 80 over 200 is like 8 over 20, which is 4 over 10, which is 0.4. Does that look right to you all? Yeah. Okay, that's what I1 is. We can solve for I3 in this equation. So I3 in this equation, let's stick with blue so you can kind of distinguish what we're doing here. Is it positive? Yes. Thank you. Negative over negative. This one should be positive. I appreciate that. Okay. In our second equation, we want to solve for I3. So I3 is going to be negative 400 amps plus 80 I2 divided by 20, because that's the coefficient here. So we end up getting that I3 is, see, 40 over 2 would be 20, negative 20. Yeah, go ahead, do the matrix version, Evan. I don't want you to think you have to use a matrix for this. That's all I'm trying to, yeah. We're going to do both. So let's see, negative 20 amps. 80 over 20 is going to be 4, so plus 4 I2. All right. And then coming to this equation here, now we can solve for I4. If you don't understand why we're doing that yet, you'll understand very quickly. So notice I have I1 in terms of I2. I have I3 in terms of I2. I'm now going to get I4 in terms of I3. So I4 here should be equal to 440 amps. This isn't going to work out very nicely, is it? Unfortunately, this equation is going to be kind of nasty because we're going to be dividing by 70. Whatever. 440 plus 20 I3 divided by 70. Why does it have to be 70? This is going to be, I'm just going to write this because I don't know how else to do it, as 44 over 7 amps plus 2 over 7 I3. And yeah, I can write those as decimals as well, but I don't really want to. That doesn't sound very fun. Now what I can do is I can say, oh, but I know what I3 is, right? I3 is just that. So I can write this equation as I4 is equal to 44 over 7 amps plus 2 over 7 times negative 20 amps plus 4 I2. And then I can expand this out, so I'll get I4 is equal to 44 over 7 amps. And now we have 2 times 20, which is going to be negative 40. So we have negative 40 over 7 amps. And then 2 over 7 times 4, which will be 14 over 7. No, 8 over 7. So then we have plus 8 I2 over 7. And we can group some terms to get that I4 is also equal to 44 minus 40 would be 4 over 7. So 4/7 amps plus 8 over 7 I2. Now we really got to check this. So I know the equation's right because we copy pasted it down, right? Is it really 440? Is that really the number you get? So what was it? It was 360 and 80. So 360 plus 80. 36 plus 8. That's got to be 44, right? Yep. It's 44. 70. Yeah, it's 70 ohms. Nothing we can do about that. Just is what it is. So that's the expression we get right there. And I guess I could factor a 2 over 7 out of this. What's 2 over 7 equal to? That's an ugly number. I'm going to leave it like this. Because now what we can do is we have basically reduced it down to where I can plug I1, I3, and I4 into my equation here, and I can simplify down because I will only have I2 left. Does the strategy that I was making there make sense before we complete this now? Okay, so let's do it. Let's plug everything into this equation here. So we're going to have negative 0.2 amps plus 0.4 I2, okay, plus I2, plus I3, which is negative 20 amps, plus 4 I2, plus I4, which is 4/7 of an amp, plus 8/7 of an I2, is equal to 0. And now we can combine like terms. For me, the easiest way to do this is just say, I'm going to have I2, and it's going to have a bunch of coefficients. What are the coefficients? There's a 0.4, plus this has a coefficient of 1, this has a coefficient of 4, and this has a coefficient of 8/7. Boy, that 8/7 makes it feel like we've done something wrong, but who knows. Plus, there's also going to be a bunch of coefficients for the other stuff. So it's negative 20 minus 0.2 plus 4/7. I'm just going to put it all together. So it's negative 20 amps minus 0.2 amps, and then plus 4 over there. Wait, there's another. Oh, this is the one that doesn't have an amps in it, right? And then plus 4/7 amps equals 0. So we end up getting all this stuff added together. We're not going to do common denominator. We're just going to add it up. So 1 plus 0.4 plus 4 plus 8 divided by 7. So we get 6.5428. I don't know how many digits to keep here. I2 is going to be multiplied by 6.543. We'll cut it off right there. And there's no unit. And that should be equal to, if we take negative 20 plus negative 0.2 plus 4 divided by 7. I didn't do that right. Negative 20 plus negative 0.2 plus 4 divided by 7. Negative 19. So we add it to the right-hand side, and we're going to get 19.63. We'll go to there, amps, which means I2 is equal to, and I'm going to use the full number of digits that I have in my calculator. So if you don't get exactly what I get, it's exactly negative 3. So that makes me feel like this is probably correct. It makes me feel like it's probably correct there, because you get exactly 3. Did you get negative 3 or positive 3? It's positive 3. That's positive 3. Sorry, it's positive. Okay, let's go back through and let's solve everything else. So now I1, right? If we plug in our answer, so we got 3, right? So 3 times 0.4 is 1.2 minus 0.2. Look at that, it's exactly 1 amp. Well, that's got to be right. There's no way it would just turn out exactly right like this. Let's do I3 from here. I3 should be equal to negative 20 plus 4 times 3. So 4 times 3 is 12. Negative 20 plus 12 would be negative 8. Okay, still going good here. We got nothing but nice round numbers. Now, could this possibly come out as a round number? It could. It might. I have a feeling it's going to be 6. 4/7 of an amp. We'll actually write this one in here. So it's 4/7 of an amp plus 8 over 7 times 3 amps. So this is 24, right? Plus 4, which is 28 amps over 7, which lo and behold actually is 4 amps. I was off. But that's what I4 is. Takes a little bit of work, right? But those are our answers. 1, positive 3, negative 8, and positive 4. Those are our answers. Yeah, whole numbers are satisfying. That's what happens when you take problems from textbooks, though, right? They work out like this. Okay, we're going to take a break, but during the break, so this isn't going to be on the video. I'm going to show you the thing I've been using to do these things, the RREF calculator. I'm just going to keep it off the video is all. So we're going on break, but I'm just stopping the video here, and then we're going to solve this with a matrix.